Now let's talk about query optimization. Any query execution can be broken down into smaller parts by using operators. Any execution plan is a pattern consisting of multiple operators connected together. Every operator has some statistics associated with it, like the number of rows that the operator produces, and this is available only if the query is profiled. Uh, it can also produce estimated rows. If Neo4j is using a cost-based compiler, we can see the estimated number of rows that will be produced by the operator. The compiler uses this estimate to choose a suitable execution plan. Each operator will ask Neo4j storage engine to do work such as retrieving or updating data. A database hit is an abstract unit of this storage engine. Different execution plans can be chosen by Cypher depending on the predicates examined, which can lead to the shortest path. The first, the fast bidirectional BFS algorithm, that is the breadth first search algorithm, is used when the predicates can be evaluated as we search for the shortest route. If there are only universal predicates in the route, for example, that all nodes have the actor label or nodes which do not have the same property, then this algorithm will most certainly return the shortest path. But if it fails, we need to examine the predicates to decide the shortest path. And in such a case, we use the DFS, that is the depth first search algorithm. There are two different strategies that can be used for execution planning. The first one is the rules strategy, in which the planner doesn't account for any of the statistics related to the nodes, but just follows a set of rules. There is the second, that is a cost-based strategy, in which the statistics for every nodes are considered by the planner while evaluating the cost for each execution plan. Hence, this approach ensures the least costly plan is selected. There is also an advanced version of query profiling for query optimization that can be used for manual query optimization. Let's look at how indexing works in Neo4j. In the earlier versions of Neo4j, it operated without any indexing. It later on introduced the manual indexing, which could be written and exploited using the Java API. The recent version has introduced the schema indexing technique, in which labels are used in the specification of indexes and for defining constraints on the graph. The graph schema comprises of both indexes and constraints. So there are mainly two types of indexes that can be defined. The first one is a single property index. Uh, a single property index is the one that is defined as a single property, as the name suggests, for any label. And as you can see, the create index example is shown, where index is created on the name of the node actor. This single property index can be used in equality searches, for which the example is shown. The As we have created an index on actor name, actors the name of actor property name, we can use it to search Leonardo in our graph database. We can also drop this single property index by using drop index on actor name. So the second type of index is a composite property index, and it is when there is more than one property used to create an index. Uh, the example for creating a composite index with name and gender is shown. We can use composite property index and equality searches as well, as shown in the example, where the property name and gender is used to search an actor. Uh, Composite indexes do not support queries as of now in Neo4js, which have predicates like exists or range queries, or that have predicates like starts with, ends with, and contains. Um, we do not need to mention which index to be used in a query, as Cypher will realize which index to use. If we want to force Cypher to use some specific index, then we can use hints. Constraints are another part of the Neo4j schema. Uh, in general, for any database, constraints are used to enforce integrity and prevent unauthorized access or manipulation. Um, Any create query in Neo4j would create a new node, irrespective of it being a duplicate of an existing record. So we can use a unique node property constraint to avoid duplicate node creation by using assert movie.name is unique. Um, the second type of constraint in Neo4j that is available is the relationship property constraint. Uh, it is used to create a constraint that makes sure that all relationships with a certain type have a certain property, and to create a node key or a node property constraint, ensuring that all nodes with a particular label have a set of defined properties whose combined value is unique and where all properties in the set are present. We can see that the example for the relationship property constraint and the node property constraint are given as shown. Moving to transaction management in Neo4j. Um, so transactions are generally, as we know, they are atomic units of work, and they're comprised in and in Neo4j they are comprised of one or multiple cipher statement executions. uh, any update query, it will either completely succeed or fail entirely. There is no partial success. So we know that Neo4j follows asset properties. Um, Cypher creates a new transaction if there is no existing transaction in the running context, and it will commit after the query finishes its execution. But if there is already a transaction present, then Cypher will not create a new one, and the query to be run will run inside this current transaction. Uh, the Neo4j comprises of three types of transactions. The first one is the auto commit transaction. Uh, the auto commit transaction is immediately acknowledged by the network, and it cannot be automatically replayed if it fails. The second type of transaction is the transaction function, which is preferred by Neo4j as the container for transactions. It will provide a clear separation of the database queries and the application logic. The last transaction is the lengthy version of transaction functions, which is known as explicit transaction. It is used to provide access to operations like begin, commit, and rollback.